Ladies and gentlemen, I would like to welcome you to my demonstration and presentation at the ACI Fall 2025 Convention in Baltimore in the United States. So I will be talking about our software ATENA, and I will describe its features for high fidelity modeling of reinforced concrete structures. For those of you who don't know ATENA, our software is focusing on advanced modeling and analysis of reinforced concrete structures, as you can see on these pictures on the right here. So we model mainly buildings, reinforced concrete buildings, and we can the focus of this presentation will be on modeling of seismic assessment, like pushover analysis, as well as full dynamic analysis. And at the end, I will also show some of our recent development for the modeling of 3D printing of concrete. So ATENA software is right now the current distribution version is 2025, and we in ATENA have recently developed a new preprocessor, and in this 2025 version we have included new capabilities to this new preprocessor, and that means if I can summarize some of the main features, it is the thermal analysis both for concrete hydration or fire modeling. We have durability, very unique durability models for simulation of reinforcement corrosion. Another new feature, very interesting one, is the Python scripting. So I will show some example of that later on. So we can develop some Python scripts to facilitate various parametric modeling. And well, of course, you can go to our website and download a 30-day trial license to try and test the software by yourself. Well, if I want to mention also some of the unique features which you often don't see in other software, you can see on this animation on the right bottom. So this is exactly the screen that you see when the program is running. So you immediately see as the program is calculating, you see how the structure deforms. You can define some monitoring points. In this case, I'm showing some load displacement diagram. And you can see very unique visualization that we have of the cracking process on the surface of the structure, but also in the interior. So we have basically two products. One we call engineering and one we call ATENA Science. I am focusing now mainly my talk on this engineering, and this engineering we are now preparing a new release which will be released at the end of this year, and the full commercial version will become available at the beginning of 2026. And in addition to static transport, we will also support dynamic analysis in this new version. Of course, even now you can perform dynamic analysis, and I will be showing some of them, but this is only available in this ATENA Science version, where we are using as a preprocessor basically a software to prepare a model. We are using a program Git. So that's the main difference between the engineering version, where we have our own preprocessor. So it allows the user to prepare the structure, run the structure, and also post-process the structure in the same transparent and user-friendly environment. So this is the main difference between this engineering version and this ATENA Science version. And our main future development is by transferring all the features which are available only currently in this ATENA Science to make them available also in ATENA Engineering. So that's what I have already said. The latest development in this new version will be also the support for this kind of complex dynamic analysis also in this ATENA Engineering. So what you see here at the bottom is an example of a 18-story building performed fully dynamic analysis. Currently this has been done in this ATENA Science version. So of course it should be important to mention how we validate our software. So of course we are continuously validating the software with known experimental data. I think you understand we are modeling reinforced concrete with cracking, crushing, reinforcement yielding, slipping of reinforcement. So all this involves very highly nonlinear material models, and it is important to validate them. So of course we are continuously validating them on existing experimental data, but here I'm summarizing our participation in various blind competitions, which of course is the best test to analyze something you don't know the result. So in these blind competitions, always the idea is to predict the behavior of some structural element or small structure. Usually it is a laboratory experiment. So here I'm summarizing some of the experiments going quite long time back. And the green points indicates the results from our software. The gray lines indicate the range of the scatter of results that were obtained by various participants. So we like to show this because I think you can see that we are consistently obtaining quite good results in these blind competitions, which is of course the best test of the software performance for these highly nonlinear problems involving reinforced concrete. Well, now I would like to show some validation which is related to this high fidelity modeling. So it is a cyclic response of these prefabricated composite concrete steel column beam connections. So it is a special type of connection involving spiral reinforcement, as you can see here. And why I'm choosing this example, because I would like to also show you how you can use some Python scripting to develop some parametric modeling or simplify the model preparation inside the software. So here we can see here's the comparison of the cyclic response of these beam column connections, and as you can see, it's a very good comparison with the experiments. And what I'm showing are two experimental results with different levels of the actual preloading. So this beam is, or this column is, of course, can be, or in real structures, it is loaded by some vertical load. So here are two situations with different loading level. This is 10% of the load carrying capacity of the beam. Here it is 50%. Of course, if you consider this higher level of preloading, the response then becomes very brittle and the structure fails right after reaching the peak load. While in the case of preloading by a lower level of load, it is possible to obtain also some post-peak response. Now I'm showing some results from or some figures from the calculation itself. So what you see here is the reinforcement and stresses in the reinforcement. Actually what it shows is the slips in the reinforcement. This is one of the unique models we have. We can include, we can model the bond failure between the reinforcement and the concrete. So this figure shows the slips along this vertical reinforcement. Well, the middle figure shows the cracking pattern on the surface, and on the right you see the cracking pattern in the interior. Of course, we can introduce some filters of the crack which can show only the most important cracks. So I would say these are again very unique visualization of the cracking, which very seldom you see in other commercial software. Now I would like to show a video animation of this process, how this model is developed with the help of this scripting system. So we can write in Python, develop a script which has been developed under this project as to simulate these. The objective of this project was to model these or to study the behavior of these prefabricated beam column joints. So you define the dimensions, the basic dimensions of the structure of the connection, and then let the parametric script generate the model, which we can now explore. We see what kind of materials do we have. So we have concrete material, we have steel material, and we have also some interface connection between the steel and concrete. All this, of course, can be visualized by different colors. This shows the definition of the material properties, so we always have possibility of figures indicating the meaning of the various material parameters. Well, then the next step is to generate the mesh. So this is done automatically by the software based on the providing meshing parameters. And the next step is to parametrically generate the reinforcement for defining radius, diameter, and the number or the inclination and the radiuses of this spiral reinforcement. So when this reinforcement is created, we can see it now in our model. So that's what this visualization is showing right now. So we see the various reinforcements generated for this connection. And again, as I mentioned, we can define the slip law. That means the bond properties of the reinforcement. We do not have to assume that there is a perfect connection, but we can say that there is some bond slip or some slip can occur between the reinforcement and concrete. So this what this example is supposed to show, how with this scripting we can create, with the scripting option, the new scripting option in ATENA software, we can define these input dialogues, and all this can be generated specifically by the user if need be, or of course we are also developing such special modules for our clients for specific problems and applications. So once the model is ready, we can launch the ATENA analysis. First, the program prepares the input data. So this shows the input file for the analysis. This is interesting to know that it is actually a text file which can be modified, edited, or even created totally separately in some other software. And now we launch the analysis. Again, I want to emphasize here this very interesting and unique possibility to see how the structure behaves even during the calculation. So you see here at the bottom we see that the iterative process is running. We are monitoring some kind of load displacement curve. So what we see on the left graph is the drift or the load with respect to the drift. And we are loading this structure element by cyclic behavior at this steel cantilever on the right, where you can see my cursor. So let me speed up the animation a little bit. Of course, this can take some time, so I am speeding it up a little bit. I think all this analysis to perform takes about 3 hours. So in the end, we obtain, well, we can see our results, and I want to skip a little bit this part of the video, and we can directly go to some animation of the whole process, which will be a little bit farther on here. So of course, after the analysis is completed, we can start we can create an animation. So this shows the animation of the behavior of this composite concrete steel connection, beam column connection. This shows, the graph shows the load with respect to the drift, and the figure shows the deformed mesh. Of course, it is very much scaled up, the deformations, and also it shows the areas, the colors are showing with red color the area where we have a full crushing of concrete. The blue colors is basically indicating intact concrete, so we can see where we have the damages, highest damages in our structure. So now I would like to also show some. So that was a cyclic model and the validation of the cyclic behavior. Now I want to go to a little bit more complex model, which is the dynamic behavior, and for that I'm using this Camus 3 benchmark, which as you can see on the right, the photo from the laboratory. So this was a scaled down model of a 5-story building that was placed on a shaking table and excited by some accelerogram. And what you see on my animation, you see the crack pattern, you see how the cracks are opening and closing. You can see the displacement at the top floor, and here is the comparison of the displacement indicated in top floor displacement indicated in black color with the experiment. So you can see a very good match. So now I would like to complete my talk and my demonstration with some practical examples, and I will focus on examples from nuclear industry. So we were involved in some consulting projects in this nuclear power plant, and you can see some models and structures that have been analyzed. So first of all, the containment was studied. So that's the top 3 figures. On the right you see the cracking pattern of the containment, and the bottom you see some buildings. So these surrounding buildings around the containment, they are of course housing or important control rooms and all important equipment. So as a part of the seismic stress checks, they were investigated against their seismic reliability. And that was done by pushover analysis. So here the results are from some pushover models. And before going into the results, I want to highlight some parts of these quite detailed, what we call high fidelity models. So for instance, this is an example of one of the buildings, and here on the top left you see the finite element model. The finite element model involves solid elements, namely for the modeling of columns and beams. And for the slabs we used 3D shell elements, which allows us to use relatively high, large, or elements with a large aspect ratio that are internally formulated as shell and plate elements, and that allows us to correctly model the flexibility and stiffness of the slabs. Well, as important of course is the modeling of reinforcement. So we see that in the important parts like the columns and beams, the reinforcement is modeled in a very detailed way using so-called discrete reinforcement approach. So you see each reinforcement bar, also stirrups are modeled in a quite detailed way. But in the slabs, you see here on the left, on the right bottom, and and also on the left right top, you see some wall elements were modeled with shell and plate elements with embedded or with smeared reinforcement options. So that means the reinforcement is not modeled by each individual bar, but is modeled as a special layer, special elements or special layers in these layered shell element formulation. Here you see some results from such modeling. So the unique cracking pattern I was already mentioning. Very interesting is also the possibility to see the stresses at each reinforcement bar. And now I would like to show an animation of this pushover analysis process. So as I told you, originally we have been performing some pushover analysis using average material parameters or characteristic material parameters, and these results were then later on used to perform some or to calculate some fragility curves. So this shows the animation from such a pushover analysis. So you see in the end we have this failure at these critical columns which fail in shear. And more recently we are now extending this study to also make full dynamic analysis. So what I'm showing you now is the dynamic analysis of such a building. It is done by implicit nonlinear solution. It has about 160,000 nodes. As I told you, it's a combination of brick elements and also shell elements. And we have about 15,000 or almost 16,000 of these brick or shell elements that are quadratic with 20 nodes. Then of course we model reinforcements, so there are altogether almost 16,000 reinforcing elements. And of course such an analysis takes a significant amount of CPU time. So just for you to have an idea how much resources does it need. So such an analysis on a relatively standard high-end desktop computer, which was a 13th generation Intel 9 processor with 24 cores and 64 gigabytes of RAM. It takes about 65 hours. So that means less than 3 days. So yeah, the last example, just more for a curiosity and as an invitation to come to visit us at our booth at the ACI convention. We are involved, or we are developing also modules for modeling of 3D concrete printing. As you can see on this structure, what is interesting is that here we actually directly create the model and also control the analysis directly from the G code. G code is actually the command file or command data file, which typically controls the printing head, the CNC machine, which actually drives the printing head and controls the printing process. So with this, I would like to thank you for your attention and would very much like to invite you to visit our booth 403 in the exhibition hall at the ACI convention. So thank you for your attention and looking forward to see you in Baltimore. Goodbye.
ATENA program produced by Cervenka company. You can find us via the website and download the program from it, or on YouTube by name Cervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.